The following teacher development program is brought to you by the MultiChoice Africa Foundation.
Yeah, that's beautiful. I mean, look at this.
Imagine this on our computer center walls. Cyberspace housed inside ancient art.
Yeah, cool. Hey, it's beautiful. What I know about arts is scary. Why don't we hire real Ndebele artists to do it for us?
Sorry, no budget. We've got to do it ourselves. Besides, the kids would love to paint with all these gorgeous colors.
How do we replicate these patterns on our walls? You know, I mean, you saw how skew our foundations were when you and I did it. This will even be worse.
Nonsense. We just need to make an accurate scale of the designs we want to use. Let's find the perfect design. What we've got to do is turn the sketch pad this way so it mirrors the way the design lies. Artists would say landscape versus portrait.
Oh, so this is 1 meter height and 2 meters wide, eh?
Yeah, and this paper is 30 centimeters wide and 20 centimeters high. So what we've got to do is determine the scaling factor. How many centimeters here represent a meter there? So, as always, we have to convert everything to centimeters because we always have to convert our measuring units to the same thing. So we start with the width. So 2 meters is
200 centimeters.
And now we need to figure out what to do with 200 centimeters to get 30 centimeters, the width of our paper. So now that is 30 divided by 200. 0.15. So our scaling factor is 0.15.
But a little bit, let me try it. Okay. So you divide the height of the paper into the height of the drawing on the wall.
No, you don't.
Why not? It's exactly what you did.
The point of scaling is to make sure that the design fits onto the paper. So you have to make sure that the largest side of the drawing fits onto the paper.
So I've got to use your scale factor. It will show us how high the drawing should be on the paper. It will tell us what 1 meter there on the wall will be on the paper.
Right.
Right, okay. So 1 meter is equal to 100 centimeters, which will then multiply with your scale factor. Okay, let's see. 1 meter multiplied by 0.15. 15 centimeters. All right. So that means every 100 centimeter height on the wall is 15 centimeters on the paper.
Right again. So let's mark it accordingly on the paper. And it should be 15 centimeters high. But the page is 20 centimeters high. So we're going to have a border there on top and at the bottom, which are 2.5 centimeters each. That's going to look like a cinema screen. Like the ones where they show the French movies.
Just draw. Give me a piece of paper.
Spoiling the fun.
All right. This is our width.
Yeah.
30 centimeters. Then now it's okay.
15.
No, it's 20.
Yes, it's 20, but it should be 15.
All right, fine. So from 20, we need 15, right?
Yeah.
And that's our height, like height, width, no?
Yeah. What you can do with symmetry and shapes is incredible. Look, this pattern reflects this one. This is what you call reflective symmetry. And this here is a reflective symmetry line.
Reflects what? Huh?
Reflective symmetry line. If you take this pattern and fold it over this one, then you get perfect symmetry.
Ah, I see. This side over this side.
Yeah.
And this is the reflective symmetry line.
Come, let's go. Look how perfectly these patterns fit next to each other. This is a perfect example of tessellation. Hey, even they're behind you.
Yay! It reminds me of the tiling exercise. They do fit perfectly. Wow, this is making me look at art design differently. It's like I suddenly see the maths of art.
Yeah, it is cool. And kids are doing it at school and they love it. I mean, my friend Patrick teaches it at Naledi High School. Patrick Madigela is a teacher at Naledi High School. Today, he's going to teach his learners about the maths of art. As a math literacy teacher, he's a bit nervous, but hopefully the students' enthusiasm for art will carry the lesson. He starts off by revising mathematical shapes with the learners.
Yeah, actually here we've got a rectangle which we use in the geometric figures.
Can somebody come and draw any geometrical figure? This is what is going to happen now. I will request one.
Once he's sure they've remembered all the shapes, he gets them to do an exercise where they have to communicate using maths language. Each learner is trying to get their partner to copy a design. They're not allowed to look at the design at all, forcing the learners to think carefully about what they say.
You must draw the kite inside the rectangle. Each corner of the kite must touch each side of the rectangle. And then you draw a circle inside.
Draw an equilateral triangle and a circle inside.
Suppose you are a designer, then you want to phone to a factory so that they can design something for you. Then since you know mathematics quite well, you can easily direct them telephonically so that they can be able to do that thing for you. Like for example, if you look at this one now, being a mathematician, then you can phone them, telling them that with the type of a figure that I like, I want a rectangle. Inside a rectangle, then you can put something like a rhombus inside. Then from there now you can put any size of any oval shape. And from there then you'll get what you want.
Next, Patrick explains the different types of symmetry. He starts off with reflective symmetry.
This picture is exactly the same as this one. If I can cut this into two equal parts, then if I put this over this one, then you see that this person automatically fits over this other one. And the other thing that we can make an example of, it is this one. If you look at this part, we have this shadow. As soon as I can obscure this other part with the mirror, but looking at the side of the mirror, you're going to see the very same size. The line here, right in the middle, that will make this shape here to fit right exactly over this other one. It is called the line of reflective symmetry. When I divide my square into two equal parts, this part will automatically fit over this one. Then if I divide it in a triangular form, this is what I will have. If I go to this direction, then I will have the reflective line of symmetry. How many lines of reflective symmetry do we have in a square?
We have 4 lines of reflective symmetry in a square.
Each learner has a square serviette and they have to fold it to find the reflective symmetry lines. Then the learners look at some African textile designs with little mirrors. Mirrors reflect, and this makes it easy to find where there are lines of symmetry. If the design looks the same in the mirror as on the paper, it means the mirror is on the symmetry line. Another type of symmetry is rotational symmetry. If you can rotate an object and it looks exactly the same after the rotation, it means that the object has rotational symmetry. We count the order of rotational symmetry as how many times it will fit onto itself until you have rotated the object a full 360 degrees.
6 orders of rotational symmetry.
We have 6 orders of rotational symmetry.
The learners make doilies by folding the serviettes on the lines of reflective symmetry and cutting out different shapes. When they unfold the serviette, they have a lovely symmetrical design. They experiment to see what the order of rotational symmetry of their doilies are by turning them.
So I have only got 2 orders of rotational symmetry because I can turn it 2 times, 1, 2, and it can be still the same.
Now, if we get the pattern that I'm making here.
Next, Patrick talks about tessellation. Shapes that tessellate are those that fit next to one another exactly, with no spaces in between. They look like a tiled floor because they fit each other exactly. Patrick explains that equilateral triangles, hexagons, and all quadrilaterals tessellate.
If we look at the circles leave the spaces in between them, and we say that circles do not tessellate.
He asks the learners to choose one of these mathematical shapes and see for themselves